Okay, cool. So it started. Hello everyone. This is the Math 2011, Math 2011 seminar. Okay. So today me and Jay are going to be presenting. So I'll be presenting curves and surfaces and most of differentiable functions, and Jay will be presenting topic 2, which is point set topology, and we'll see how much of integration that he can get done. Okay, so we're starting with curves and surfaces. So curves. The definition is that the parameterization of a curve in Rn is a vector valued function. So where I is an interval on R. So we have I as an interval on real numbers. So for example, it starts with A and ends in B. And vector valued function just means that the range or the output is going to be a vector or a set of vectors. A multiple point is a point through which the curve passes more than once. So if we have a curve which is like a circle and goes through once and it goes through again, these points are going to be multiple points because the curve passes through them more than once. And a curve is closed if the point at the beginning of the interval is equal to the point at the end of the interval. So if we have a circle that just goes through once, so CA is here and CB is also here, that just goes through it once, so it's also going to be a closed curve. Limits and calculus for curves. So the definition, let C, which goes from an interval to Rn, be a curve with n components, and let A be an element of the interval. So the limit exists so the limit for the curve right here is only going to exist if the limit for each of the components also exists. So for every component, so C1, C2, all the way down to Cn, if their limit exists as, for example, t approaches A, then we're also going to have a limit for the curve as t approaches A. A similar thing for the derivative of the curve. So the derivative of the curve only exists if a derivative for every component of the curve also exists. So the derivative of the curve can be interpreted as the tangent vector or the velocity at t. So, and if we want the speed, so that's a scalar value. So we just find the distance of that vector. So speed is going to be equal to the distance of this tangent vector or velocity vector. And the second derivative of the curve is the acceleration vector. Okay, so surfaces in R3. So we can express surfaces in 3 ways. So we can express them explicitly as a graph. So as a function of 2 variables, so x and y. We can express surfaces implicitly. So that's where we have a set of all the values where this function is equal to 0. And we can express surfaces parametrically. So if you have the surface, you have 3 sets of equations. So you have x equals something, y equals to something, and z equals to something. So you have these 3 sets of equations to parametrically represent a surface. Okay, so let's get into the first exam question, past exam question. Suppose S is the surface given by x squared plus 3y squared minus z squared equals to 1. Sketch the intersection of S with the xz and xy planes. Label your axes carefully. Identify intercepts and asymptotes, if any. Identify known curves by name. Okay, cool. So we have here the intersection of a surface with the xz and xy planes. So if we just construct the xyz axes, so we have the x-axis here, the y-axis here, and the z-axis here. So the xz plane looks like this, and it's gonna, so the xz plane exists when the value of y is set to 0, and the xy plane, which is this, that's when z is set to 0. So for the xz plane, we're going to sub in y equals to 0 to get x squared minus z squared equals to 1. And for the intersection with the xy plane, we set z equals to 0. So the intersection of S with the xz plane will occur when y equals to 0 and is a hyperbola. So we get the hyperbola x squared minus z squared equals to 1. The intersection of S with the xy plane occurs when z equals to 0 and is the ellipse x squared plus 3y squared equals to 1. Okay, so now we have to sketch these. So let's start off with the hyperbola x squared minus z squared equals to 1. The x-axis here, z-axis here. The intercept, so when z equals to 0, we have x equals to 1 minus 1. And we know from earlier math, like high school or whatever, we know that asymptotes for this hyperbola is going to be x is equal to z. X equals to minus z. It looks a bit like this. And then the second intersection, we have an ellipse. So when y is set to 0, we have x equals plus minus 1. And when x is 0, we have y is plus minus 1 on root 3. Cool. So this comes to the end of curves and surfaces. So Jay is going to take over from point set topology, so the second topic, and he's going to cover a bit of differentiable functions. So he's going to do differentiability and affine curves. So I'll hand it over to him, and I'll come back after.
Hello, give me 1 second. I need to connect my tablet. Give me 1 second. I need to. Let me find the connecting thing. Sorry, give me 1 second. I think I might just connect to my PC instead, because I cannot find my adapter. Sorry. Let me stop streaming here.
Alright, sorry about that. I didn't know that I was missing my adapter. Okay, yep. So as Jerry said, I'll be picking it off from points at topology in topic 2. So I guess we'll go straight to that. Topic 2. Okay, so firstly, in points at topology, we're going to define a concept called the epsilon ball or the delta ball. In essence, its notation is B of a point like a position vector in Rn with a radius of epsilon. And graphically, all it's saying is you have a point A, and around it you have a ball, and the radius is epsilon. Okay. Now this is in 2D space. In 1D space, or in other words, in the number line, it would just really be the line interval around A. And in 3D space, it would be like a sphere. Yeah, a sphere around A. Okay. So in essence, regardless of which dimension you're in, it's really just the local neighborhood around a position vector A, or X, or whatever you want to define this as. Next, a punctured ball is a very similar concept to the ball. It's simply just the same thing, but at the very center, where the point A is, it's now open instead. Okay? But it's the same thing. Okay? So that's the ball. Next, let's move on to open and closed sets. So let's go through some definitions. If X is an interior point, then that means that there always exists an epsilon arbitrarily small enough such that the entire ball around X fits within your set omega. So for example, if our omega set looks something like this, let's call this set omega, and we pick some point X on the inside, it's an interior point because we can find a epsilon ball around X that's small enough such that it fits within our entire set omega. Okay, that's what an interior point is. Now, your set omega is open if every point is an interior point. That sounds a bit arbitrary. What does that mean? For example, the set I drew here, this omega set, is already an open set. Why is that? That's because, for example, this point's an interior point. If I selected some other point, let's say y, that's also an interior point. And even if I select something that's very, very, very close to the boundary of omega, so let's say something here, I'll call it z, I can still find a ball that's arbitrarily small enough such that the entire ball will fit within our set omega. Okay, that's what it means for a set to be open. If every point in the set can be considered as an interior point. Now, the set omega is closed if its complement is open. Okay, so what does that mean? It's kind of like a cop-out definition. For example, I'll maybe add a new page and draw another example. So edit pages, insert a page. Okay. So for example, again, a new set, I'll maybe call it omega dash points, because for example, in this blue set here, if I chose a point on its boundary, it's not an interior point, because no matter how small I draw the ball, part of it will be on the inside, but the other part of it will always be on the outside of your set. Okay. All right. A set is closed if and only if it contains all its boundary points. I also just mentioned that. Basically, if your entire set has closed lines or thick lines on the perimeter rather than dotted lines, it's a closed set. Okay, and some like two useful theorems is that a finite union or intersection of open sets is still open, and a finite union or intersection of closed set is still closed. Okay, let's have a look at example 1. Use the definition to show that the set, the line interval -3 to 1, is not open. Okay, so let's have a look at visualizing this first. So let's draw the number line. Okay, let's say this is 0, this is 1, this is -1, this is -2, and this is -3. Okay, so this interval here would be going from -3 to 1. Okay, now notice that this set will go into proving it more properly with like why it's not open. It's in a sense not open and not closed, right? So I guess that gives us another fact about open and closed sets. A set doesn't necessarily have to be open or have to be closed. It can be neither, right? In this case, it's neither, because on this hand, I have an open interval, but on this end, I have a closed interval. So it's neither fully closed and neither is it fully open, all right? So for example, why is this not open? If we just think about it, well, for example, if I just picked this point here at -3, clearly the local neighborhood around this point -3 won't fully be within our set from -3 to 1, right? Part of it will be on the outside, okay? And that's exactly our approach when we're going to try to prove this question, okay? So let's move on to the next page. Yep, so I guess some more definitions here. Firstly, if a set is open, this condition must hold. For any x we choose in the set, there must exist an epsilon small enough or arbitrarily small enough such that the ball fits within the set. And if a set is not open, then we're trying to show that we can find some counterexample x in the set such that no matter how small we choose epsilon to be, we still can't fit the ball within our set omega. Okay. So in our question, like illustrated before, let's just choose the point -3. Right, so remember our diagram looks like this. -3, -2, -1, 0, 1. Okay, so let's just say we choose the point -3. Okay, then no matter how small we choose epsilon to be, so epsilon can be any number greater than 0, no matter how small we choose epsilon to be, if we pick y0 as a new point to be x0 minus epsilon 2, so this is -3 minus epsilon 2, this point will always be within our ball or our local neighborhood around x0 with a radius of epsilon. Because, for example, if this was our neighborhood that we defined it to be with a radius of epsilon, -3 minus epsilon 2 would be right here, right? It would always still be within our local neighborhood. But the issue is, this point is not within our line interval from -3 to 1. This is our set, omega, and it's not within there, right? Which means the very existence of this point y0 implies that we cannot fully fit any ball, or in this case line interval, around -3 into -3 to 1. Therefore, the set's not open. Okay? So for a question like this that's asking us to prove something that's not open, all we need to do is provide a counterexample, right? All we need to do is provide an example where we can pick a point where it's not going to have its ball fully enclosed in the set, then we're done. Okay. Okay. Next, let's have a look at limits of sequences. For a sequence xi in Rn, x is the limit of the sequence if and only if, for all epsilon greater than 0, there exists an n amongst the integers, such that for all k greater or equal to this n, our sequence lies all within the epsilon ball around x. So again, visually, what does this mean? I'll use blue again. If we have a ball around our point vector x with radius of epsilon, okay, so this is epsilon, we're saying that there's some sequence of x's such that, maybe I'll use a different color for this. I'll use red again. Such that it begins to spiral in closer and closer and closer and closer and closer and closer towards our point vector x, right? So it's saying at some point, in this case it would be this point here, at some point, all of the points in the sequence will lie within our epsilon ball, yeah? And that way, it's kind of implying that it will eventually begin to spiral closer and closer and closer towards our point vector x. And in that case, this would be our limit point. Okay, this x here would be our limit point. Okay, a sequence xk converges if and only if the components of xk converge to the components of x. That sounds a bit arbitrary at the moment. We'll come back to this a bit later when we look at useful theorems related to limits. But for now, let's just move on to the next point. This x here is in a sense called the limit point of the set. And loosely speaking, it is a point such that it can be described by other points in the set arbitrarily close to it. For example, think of 0 on the real number line. Okay, so what does that mean? For example, if I draw the number line again, this is 0, and this is, for example, 1, -1, and so on. If you consider the set 1 on k, as k gets larger and larger, in a sense, this sequence here kind of describes what happens around 0, right? If you imagine k going 1, 2, 3, 4, 5, 6, all the way to infinity, this sequence is going to get closer and closer and closer and closer to 0. So in a sense, the point 0, or the value 0 on this real number line, is described by our sequence here. Yeah? So it's a limit point if it can be described by other points in the set, like getting arbitrarily close to it. Okay? And our last stop point is, to show a point is not a limit point, show that there exists an epsilon greater than 0, such that for all n within the integers, there exists a k greater or equal to n, such that xk is not in the ball around x. So it's kind of like just a complete opposite of what I drew here. It's saying that we have a point x, an epsilon ball around it, and you have some sort of sequence. But the sequence eventually comes out of the ball again, right? Then in that case, we don't have a sequence that tends toward a limit point. All right? Okay. A few more definitions, then we'll move on to some examples. The interior and boundary. The interior of omega is the set of all interior points of omega. That's pretty self-explanatory. The boundary of omega is the set of all boundary points of omega and is denoted by delta omega. And the closure of omega is just the union of both, right? So if you have a graph omega, then the interior point is just every point on the inside. The boundary is just the perimeter. And the closure is just this entire piece. Okay. Some lemmas. X is an interior point of omega implies that X is a limit point of omega. X is a limit point of omega implies that X is a boundary point or an interior point of omega. X is in the closure of omega implies that there is a sequence in omega with limit X. It's good for you to think about these lemmas. I won't go through all of them, but maybe we'll have, I guess, a further thought on the first dot point here. I'll add a new page so that I can explain this a bit more. Okay, so here we're having a look at x is an, oops, I need to drop this out, is an interior point, implies that x is a limit point. Okay, so why is that? Let's just draw a set first. So let's call this omega. Okay, so it's saying any interior point in omega is actually also a limit point, right? So it's saying that if I pick some point x and I draw a epsilon ball around it, then I can always find some sequence xk such that it will tend closer and closer and closer towards x. Okay? Now, why is that the case? The proof is quite simple. Simply choose the sequence that will always work. In this case, if we have an epsilon ball around our red point here, x, we can just choose the sequence. We can just choose our sequence xk to be our point x plus epsilon on k, right? Then if you think about it, as k gets larger and larger and larger, the sequence will always be contained within our epsilon ball, and furthermore, it will spiral closer and closer and closer towards our red point x here. Okay? So yeah, so this is how you could think about this lemma here, right? Graphically, it looks like this, and a bit more theoretically, you can just consider this sequence here in particular. Okay? Limit of a function at a point. I see that someone said, anyone else hearing ringing from the live stream? Yeah, I think that may be an issue with my microphone. I apologize for that. Yeah, I think there's something wrong with my headset where every so often there would be a bit of a ringing noise. Yeah, sorry about that. Okay. But moving on, so limit of a function at a point. So it's saying that a function converges to the point B as x approaches A if for all epsilon greater than 0, there exists a delta greater than 0 such that for all x in the set omega, x being in the punctured ball around A and in omega implies that fx is in the ball around B. So it's basically saying that if we have the pre-image here, oops, the pre-image here and our image here, or I guess domain and codomain, if you have a punctured ball around A and you apply the function f and map it across, then it will always lie within our epsilon ball around B. Okay, so every point in the pre-image here, when applied to f, will map over to a point within the epsilon ball around B. Okay, and if such a B exists, then B is unique, and we write that the limit of fx as x approaches A equals to B. Okay. So now we move on to the useful limit theorems I was talking about before. The first one here, limit of fx as x approaches A equals to B, if and only if limit of fi of x as x approaches A is equal to bi. This is the exact same thing as I mentioned back up here. In order, all this stuff is not in 2011. Yeah, I believe point-set topology is barely covered in 2011. Yeah, this seminar is a hybrid between 2011 and 2111. Yeah. Okay, so we'll go back down. It's saying, for example, if I have the function fx, and let's say the function is f1x, f2x, f3x, for example, right? It's like a vector function where there's different components, f1, f2, f3. It's saying that this, so as x tends towards A, this only equals to B if So yeah, this only equals to b as x approaches a if f1x tends towards b1, f2x tends towards b2, and f3x tends towards b3, right? So if you want this entire thing to tend towards b1, b2, b3, it's simply saying that every single component must tend towards b1 for f1 to b1, f2 to b2, f3 to b3. Okay? Second dot point, or second theorem here. The limit of fx as x approaches a equals b if and only if the limit of fxk as k approaches infinity equals to b. So this goes back to our previous little topic where we talked about sequences. It's saying that if we can construct any sequence of xk that approaches a, then the limit of f at this sequence must also equal to b. Okay, we will see an example right after relating to this theorem, so hopefully that will make more sense once we do that. Okay, yeah, but basically it's saying if, for example, I have my xy plane, we're considering whether some function tends towards this point here, let's call it b. We need it to tend towards b in all possible directions. So this way, 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 this way. How many ways you have in your function, they all have to tend towards b as you get closer to b. Right? It's similar to saying in what you learned so far in like 2D space where a limit has to approach from the left and the right and equal the same thing. Same logic there. Your sequence from the left and from the right must tend to the same thing. Okay? And these are just algebra of limits. Sum of limits is just a plus b if the limit of fx equals a, the limit of gx equals b. The product of limits is just ab, and the division of limits is just a on b, given that b is not equal to 0. Okay. Last theorem before examples is the pinching theorem. Okay. So let a be a limit point of omega, and let f, g, h be functions from omega to real numbers, such that there exists a delta greater than 0, such that for all x that lies within the delta ball around a. Okay. Then, if we have this condition here, where fx lies in between gx and hx, then if gx is equal to b as we take the limit, and hx is also equal to b as we take the limit, then that kind of, in a sense, like clamps fx together, or like pinch fx, and fx must also then be equal to b. Okay? It's kind of like saying if you have some variable and it's greater or equal to 1 and less than equal to 1, then x must just be equal to 1. Yeah. Okay. Our second example, show that the following limit does not exist. Okay, so we have limit of xy approaching 0, 0, and the function is x plus y over the absolute value of x plus the absolute value of y. In this question, we will make use of the second theorem shown above, so the second useful limit theorem, which was this one. Okay, so we're going to construct different sequences for x approaching a, in this case for xy approaching 0, 0, and show that the limit at those two different sequences ends up being two different values. Okay? Yep, so as we describe here, our strategy would be to find two particular sequences such that the limits do not equal. Okay? Let's first choose xk equals to 1 on k and yk equals to 0, for example. Clearly, as k approaches infinity, this sequence will approach 0, 0. Okay, that's what we want, because we want xk, yk to approach 0, 0. Let's now compute the limit of this sequence. So if we take this limit, we have the limit of k approaching infinity of x. So this used to be x. K becomes 1 on k. This used to be yk. As now becomes 0. So the same thing here. This used to be xk. This used to be yk. So 1 on k plus 0 over the absolute value of 1 on k plus 0. That's obviously just 1, right? 1 on k over 1 on k. Okay. We now look for another sequence that also tends towards 0, 0, but then returns a limit besides 1. Okay, so we want to find another sequence such that the limit is not equal to 1. Okay, let me rub this out. Okay, so let's move on. This time, let's just choose xk equals to -1 on k instead. The intuition behind choosing this value is just because, well, here I noticed that on the bottom there's absolute values. So I'm just guessing that if I choose negative of what I chose before, it would result in a different limit. Okay. Let's see that that works out. When we plug it into our function, we get -1 on k plus 0 over the absolute value of -1 on k plus 0. Obviously, this becomes -1 on k over 1 on k, and so that becomes -1. And so yeah, therefore we've proven that the limit does not exist because we can choose two different sequences, one approaching from the right, which is 1 on k, and one approaching from the left, which is -1 on k, and they don't both tend towards the same value. Okay, so one tends towards 1, and the other one tends towards -1. Next, example 3. Given that the absolute value of this function is less than or equal to 1, show that this limit is equal to 0. Okay. Know that in this question, we would want to use the pinching theorem. Okay, and the intuition behind choosing this would be we are given information regarding the absolute value of a significant proportion of our limit already. So if we go back up, as you can see, the only difference between the information given and the limit we want to look at is that it's times by an extra multiple of x, and that's it. Right? So we might as well use pinching because they have already given us information about this absolute value being less than or equal to something. Okay. Okay, so if we could just show that the absolute value of our limit also tends to 0, then we have shown that our limit tends towards 0, right? So firstly, yep, like I said before, notice that this is really just x times the thing we have in our absolute value. And so if we then take its absolute value, we obtain this result. So we take the absolute value of this, which then becomes this. But then, since we're given that this is less than or equal to 1, we have that this entire thing is less than or equal to the limits of absolute value of x. Okay? And by pinching theorem, this equals to 0. If you're not sure how this is pinching theorem, since this is absolute value of x, we essentially have that this thing here is less than or equal to x, and is less than or equal to -x. Yeah. So as x approaches 0, then both sides tend towards 0, so this thing on the inside must also be equal to 0. Okay. All right. That's it for our limit theorems. Let's move on to continuity. So let A be in the set omega, and a function that sends you from omega to Rm, and it's continuous at the point A. It's continuous at the point A if the limit of f as x approaches A is equal to fa. Okay, and the function is said to be continuous in general if it's continuous for all possible a's. All right, continuity is like an extension of limits. It firstly requires that the limit exists, and secondly that the limit actually equals to the value at that point. Right, so it's very similar to your understanding of continuity from like 1131 or 141. It's kind of saying that left-hand limit has to equal to right-hand limit, and furthermore, the limit there has to equal to the actual value there. Okay. Now, there's also an epsilon delta interpretation of continuity, and it's saying that for all epsilon greater than 0, there must exist a delta greater than 0, such that x being within the delta ball around A and in omega implies that fx lies within the epsilon ball around fa. Right? So it's very similar to one of the definitions I talked about before, except this time it's not punctured. Yeah. So it's just a delta ball around A. You map it by f, and it becomes an epsilon ball around fa. Okay. All right. Now we're going to properly define the pre-image. The pre-image is, so suppose that omega is in Rn, and the function sends you from omega to Rm. The pre-image is basically, in a sense, the inverse map of the set U. Yeah. So F inverse of U would be your pre-image. A theorem that we have is that if F is continuous on omega, F is continuous on omega, if and only if U is open in Rm implies that the inverse of U is open in Rn. Okay. Suppose omega is open. If Fa is an interior point of F omega, and the epsilon ball around Fa is in F omega, then A is an interior point of F inverse, B Fa epsilon. Okay. All right. Let's move on to example 4. This one is a non-exam question, and it's essentially asking us to prove, I believe, this theorem here, okay? Or like some version of this theorem here. Okay. So if S is open, and if F is continuous, what is known about the pre-image of F inverse of X? So it's basically saying, so eventually we want to prove that if F is continuous, then S is open implies that F inverse of S is also open, right? It's kind of like a rewording of this theorem here. Yeah. Okay. So how can we prove that? This proof will require some more in-depth application of the theory involving like epsilon and delta balls. Okay. Let's have a go. Firstly, let's denote x0 as being some arbitrary element within the pre-image of S. Then, of course, we have that f of x0 is within S, right? We just, I guess, take the inverse over. Okay. Now note that we have two pieces of information to work off. Firstly, we have that S is open. If S is open, this implies that we have some ball around fx0 that is a subset of S, right? Since fx0 is within S and S is open, then that means there must be some ball around fx0 that is fully enclosed by S, right? Because this must be an interior point. Okay. Next piece of information is that F is continuous. By our epsilon delta interpretation of continuity, we have that for epsilon greater than 0, there must exist some delta greater than 0, such that if our point x is within the delta ball around x0 and in S, we have that fx is within the epsilon ball around fx0. Okay, that's just the epsilon delta interpretation, basically regurgitated, right? Now, since this applies for all epsilon greater than 0, we can choose epsilon to just be arbitrarily small. In this case, we'll just choose epsilon to be particularly smaller than the r that we chose back up here. Okay. So what do we have now? Combining these two results together, we have that fx is within an epsilon ball around fx0, which is a subset of a r ball around fx0, which is within S. Okay, so recall that we have that fx is within an epsilon ball around fx0, but since we're choosing epsilon to be less than r, we might have a situation that looks like this. This is your r ball, and then this is your, let me choose a different color. This is your epsilon ball. Okay, right? So our epsilon ball is completely contained by our r ball. Okay, and furthermore, our r ball around fx0 is a subset of S because we have S is open. Okay, and so we have that X is within the F inverse of S, right? So if now we have this result, right? So we take the inverse on both sides. So X must be an element that is, whoops, why did I write subset here? I mean element. So X is an element of F inverse of S. All right. What does that mean? We have that from the epsilon delta interpretation. X must have been in the delta ball around x0. But we also now have that as a result of continuity and openness of S, X must be in the preimage of S. And so it's saying that you can always have a delta ball around x0 that is in the subset of the preimage of S. And this is basically the definition of an interior point, right? So that means x0, no matter what we choose it to be, will always be an interior point of the preimage of S. And so the preimage of S is open. Yeah, because every point in the preimage of S is an interior point. Okay. All right. Compact sets. A set omega is bounded if there exists an M in the reals such that the distance between our point X and the origin is less than or equal to M. So if we have, I guess some set, let's say like this. For example, I can choose M, like the distance M to be this far out. So this here has a distance of M, then this circle with radius of M and encloses our entire set omega. So omega is bounded. Okay. A set is compact if it's closed and bounded. And we have a theorem here. If our set K is in our set omega and K is compact, then f of K is compact if f is continuous. Okay. Path connected sets. A set omega is said to be path connected if for any x and y element we choose in the set omega, we can find some path between any 2 points in the set, and this path is continuous. Okay, so if we have, let's say, a set that looks like this, just a circle, this set's a circle, we can always pick any 2 points in our set, x and y, and we can always find some path between x and y, right? We can, for example, just pick that path there, or you can pick the path where you go right and then go up. Okay. Let omega be an Rn and f be a continuous function. Then it's a very similar version of this theorem here. If B is in the set omega and B is path connected, then f of B is also path connected. Here is just an example of what I drew up here. For example, if you just have x and y in the R2 plane, let's say, x, y, and you want to pick any 2 points, you can always just connect it by the straight line from x to y. Okay. All right. Example 5. Use the definition to prove that the unit square S, where R is between 0 and 1 and theta is between 0 and 1, is bounded. Okay. So essentially our diagram will look something like 1, 1. We have a unit square here. That's closed. Okay. We want to show that it's bounded. This should be relatively easy, right? We can just choose any bigger radius. Let's say we choose 2. Then this circle encloses our unit square. And so our unit square is bounded, right? We could have chosen something a bit more specific, like let's say root 2 plus epsilon or something, because at the end of the day, this diagonal here only has a length of root 2, right? But we can just choose 2, because we have a choice anyways, right? Part B, use the definition to prove that the unit square S is path connected. So again, if you have a unit square like this, and you pick any 2 points, you can always just go in a straight line from the first point to the second point and show that's path connected. Right? Let's do something a bit more exotic. Let's try do it with a piecewise function, because sometimes these questions may be a little bit harder in exams. And I'll go through it here. Okay. So rather than going by a straight line, let's go by the example I showed you before, where you go with 2 different paths. So let's say this is the first point. Let's call it x. This is the second point, y. Instead of going in a straight line like this, let's go like this. Go right, and then go left. Right? How would you define this as a function? Okay. Well, firstly, note that you have a phi function with a variable t, and t ranges between 0 and 1. And we needed two particular conditions. We needed phi of 0 to equal to the initial point, and phi of 1 to equal to the end point, right? So we need phi of 0 to equal to x, phi of 1 to equal to y. In this case, x is x1, y1, and y is x2, y2. Okay? All right. So we only have the range from 0 to 1 to work with, but we want to incorporate two actions, right? We want to incorporate moving right and incorporate moving up. How can we do that? We'll do that by splitting off our t to 0 to half and half to 1. This interval will take care of moving towards the right, and this interval will take care of moving up. Okay? So how do we move to the right? Right? So this point here is at the moment x1, y1. This point here would become x2, but still y1. And this point here would finally be x2, y2. Right? So to move to the right, we need to move over by our x coordinates. Right? So we have a line interval connecting x1 to x2. Note that here we don't just use t, we use 2t because t only goes up to half. Yeah. So now, for example, if I choose t equals to half, this top piecewise bit would become 1 minus 2 halves x1 plus 2 and then half x2. And it would take us to what? 1 minus x1 plus x2, which should take us all the way to this point here. Okay. And then similarly from half to 1, same thing, but now we're moving up. And again, we choose 2t rather than just t because t only goes from half to 1. Okay. Okay, part C. Find the image of fs where fr theta equals to r cos pi on theta on 2, r sin pi theta on 2. So hopefully you guys can recognize from this that it's similar to polar coordinates already. So it's going to have something to do with a circle, right? To actually find out how it looks like, let's convert this parametric equation into a Cartesian equation. So let x equals r cos pi theta on 2, y equals r sin pi theta on 2. Then x squared plus y squared equals to r squared, right? If you just square x squared, you would get r squared cos squared pi theta on 2. Y squared equals r squared sine squared pi theta on 2. Add the two equations together, then cos squared plus sine squared equals to 1. So you just have this circle here with radius r. Okay. But furthermore, note that again we had the conditions that r range from 1 to 0 and theta range from 0 to 1. Yeah, from up here. And so our angle can't range the full circle. It only ranges from 0 to pi on 2. And furthermore, our radius ranges anywhere between 0 and 1. So what we really have is just the first quadrant. That's what our image looks like. Okay. Okay. Yep. So as we said here, because of these conditions, the radius only ranges between 0 and 1, and our angle only ranges from 0 to pi on 2. Okay. And finally, for part D, is fs path connected? Explain. We can just refer back to this theorem here, right? We had proven that S is path connected, and furthermore, S lies within our omega. In this case, it would just be r squared, right? So we have that S lies within our larger omega set, and furthermore, S itself is path connected. Therefore, Fs is path connected. Right? So we just make reference to that theorem, and we're done. Yeah, we have S is within r squared, and S is path connected, so Fs is also path connected. All right, let's move on to the next section, differentiable functions. I'll go through the very beginning of this on partial derivatives and differentiation. Then I'll pass it back over to Jerry after. Okay, so let's get started. First definition we have is partial derivatives. Let the point A be an omega and f be a function from omega to r with the coordinates xi and standard basis vectors ei. Right, so again, if you forgot what standard basis vectors are, for example, E1 is just 1, 0, 0, blah, blah, blah. E2 is just 0, 1, 0, blah, 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 and so on. Okay. The partial derivative of f in direction I is defined as this. So it's really just, I guess, kind of like first principles here, right? So this is just the direction of xi. Okay. Yep, so I guess a note here is it's pretty much the same as taking a derivative, but only with respect to the variable defined here. Okay. We have a Jacobian matrix. This is pretty much the matrix where you chuck in all your partial derivatives, right? Your function derived in terms of x1, x2, x3, x4, all the way to xn. Then your second component of your function derived in terms of x1, x2, all the way to xn, all the way to the mth component of your function derived by x1, x2, all the way to xn. Okay. We have a theorem here. Omega is a set in Rn, and A is a point in omega, and it's an interior point, and f is a function from omega to Rm. If f is differentiable at A, then all partial derivatives exist at A, and dfa equals jfa. What is dfa? It's kind of like your, I guess, your derivative matrix, right? So it's pretty much saying that the Jacobian is your matrix, your directional matrix, or can't say the word, or derivative matrix. Okay. Affine maps. A function t is called affine if there exists a y0 and a linear map L such that this happens. Okay, that's just a definition there, right? So you basically have a point vector, a point vector, so a position vector or point vector, and then a linear map. Okay. Okay, a function f has an affine approximation at a point A if there is a matrix A and a vector B such that this happens. All right, so it's basically saying that our fx is very closely approximated by ax plus b, thus a affine approximation, because affine in a sense means linear. Okay, and this denominator here is just a weighting to scale it. Okay. The affine approximation is this, yep, as I stated here. Okay. Differentiability. A function f is said to be differentiable at a point A if f has an affine approximation at A. So this is practically an extension of what is shown here. Okay, so in this case, it's saying fx can pretty much be approximated by fa plus the Jacobian, or in other words, the directional matrix, times x minus a. Right. So again, this is like your position vector. This is like your direction, and this is your just x minus a, right? Okay. So it's quite similar to what you learn in linear algebra in terms of point vector plus gradient times x minus a. Okay. Yep. So it's saying if this limit equals to 0, in other words, we can pretty much approximate fx by this affine map, then we have differentiability. Okay. So I'll go through one question in this topic, then I'll pass it back to Jerry. Find the best affine approximation to the function f, defined by first component being x squared plus y squared, second component being hyperbolic sine x squared minus y squared at the point 1, 1. Okay. Okay, yep, this is just jotting down what we said before. Okay, so let's start off by computing the Jacobian. So the Jacobian, remember, is each component and you take its partial derivative. So it would be, in this case, if this is f1 and this here is f2, it would be derivative of f1 in terms of x, derivative of f1 in terms of y, derivative of f2 in terms of x, and derivative of f2 in terms of y. Okay? So we differentiate x plus y squared in terms of x, you get 2x. Differentiate it in terms of y, you get 2y. Differentiate hyperbolic sine x squared minus y squared in terms of x, you get this. Differentiate by y, you get this. Okay? And so now if you plug in our point, which I believe was 1, 1, yep. So you plug in xy equals to 0.11 into here, you get 2 times 1 is 2, 2 times 1 is 2, 2 times 1, and then cosh of 0 is 2, and then negative 2 times 1 cosh of 0 is negative 2. Yep. Okay, and this here was just FA. So in this case, it's just plugging in 1, 1 into here. So you have 1 plus 1 is 2, and sine of 0 is 0. And so you can expand this all out, and you end up getting this value here. So it ends up being that. Okay? And that pretty much concludes it for my bit at the moment. I'll pass it back to Jerry, and then I'll come back at the end if we have time to do some topics about integration. Okay? So I'll end my stream on my end, but please just wait for Jerry to come back on. Okay?
Cool. So if the timing is correct, it's back to me. So I'm going to cover the rest of differentiable functions. So it's going to be more of like a 2011 focus for me. So I'll still cover some of the theory slides that's more focused on 2111, but yeah, I'm going to be mostly solving questions that come out in 2011 papers. Okay, cool. So let's start with the chain rule, the definition. So if we have f, which is differentiable at a point A, and g that is differentiable at fa, we know like the result that the derivative of g of f at A is equal to the derivative of g at fa and the times the derivative of f at A. But if we look at it in more of like a 2011, how it's used in 2011. So let's start with the theorem. Suppose that f is a differentiable function of two variables x and y. So we have these two functions, x, y, and x and y contain two variables s and t. So they contain here s and t. So if we want to find the partial derivative of f with respect to s, so that's kind of like how sensitive this whole thing is to changes in s. So we need to find how sensitive the function is to the x function, and within that x function, we want to know how big s makes an impact. And for the y function, we did the same thing. So we want to see how important the y function is for f, and inside y, we want to see how sensitive y is to changes in s. And for t, it's just pretty much the same logic. So we just switch around s and t. Okay, so this exam question. Use the chain rule to find dz dr, dz ds, and this, which is right? It's not two dz's. In terms of, so we have a bunch of partial derivatives of f with respect to u and v. If we have z, so z is a function of u and v contain r and s. So if we want to find dz dr, it's pretty much the same thing as we showed in the previous slide. So if we want to find how sensitive z is to changes in r, we want to know how important each of the u and v functions are, and within the functions how important changes in r are. So here we have df du, so we know that's the partial derivative of df du, that's equal to 2. And df dv, no, dv dr, that's 1. So that's what we have here. And dz ds, so it's the same thing, except instead of r now, we have s. And df du ds is here -1. And dv ds is 2s. So yeah, so this is the answer for this. So now we want to find this second order derivative. So as we've said before, this is equal to this. That's just like the notation. There aren't like two z's. And here we can use, we've already solved dz dr, right? We've solved it right here. So we can just sub in this result right here. So now and then we just expand it over the brackets, the ds. So we just multiply dds to both of these terms. Okay, so the next part is probably the trickiest part. So this part corresponds to this, and this part corresponds to this part. So the reason why we have to split this again into two parts again is because df du, if we look back up here, df du is still going to be a function that contains both r and s. So if we want to find the derivative with respect to s, we're going to have to split it up. So what happened here was that if you just multiply this, we get dds. So that's essentially what we've done. And then we just have to break it down now. So, oh, and also this turns into, and this part is going to turn into, yep. So now we have du ds. So we want the results in terms of partial derivatives with respect to f. So we have to break these up. So what's du ds? Du ds is -1. dv ds, that's 2s. Du ds, that's -1. dv ds is 2s. And then we just factor it in. So -1, 4s, dv ds is 2s. Yeah, and it just simplifies into this. Cool. So now we move on to the gradient. Okay, so the definition is that for a function, for a real valued function, the Jacobian is referred to as the gradient of f. So nabla f is equal to, so if we just look at this with a different type of notation, this is f x1. Usually in math 2011, we only work around with 2 variables, sometimes 3. So yeah, usually we just cut it off at where x1 is x and x2 is y. But you can generalize it to, obviously, n components. So if we look at the MATH2011 definition, suppose f is a function of 2 variables, and fx and fy are continuous at ab, then the gradient is nabla f. So that's just fx, fy. So the gradient is the direction of the steepest increase at a, so at a point a. The gradient is going to be the direction vector to where the function is increasing the most. So that's the first useful result we need to keep in mind. And the second thing is it's orthogonal to the tangent plane at that point. The tangent plane can be given by the equation. Okay, so if we want to know why the gradient is orthogonal to the tangent plane at a point, we just have to, so if we have a function implicitly, it's equal to a constant, and then we differentiate both sides, we get 0, and here we're going to get nabla f and the gradient. So yeah, and then since the dot product is, well, not the gradient, the tangent plane. So because the dot product is equal to 0, they're orthogonal to each other. Okay, so let's apply these results to an exam question. Does the surface, so that's the first surface, and this sphere touch tangentially at a point? And prove your answer, okay? So we have like a surface. We have a surface and a sphere touching at this point. And what the question is asking is, do they touch tangentially? So essentially at the point where they touch, do they share the same tangent plane? So one way we could go about doing this is calculating the tangent plane using this equation for both the surface and the sphere at that point. But we also know that the gradient is the normal to the tangent plane at the point. So a faster way to do this question is for us to prove that the normals of the surface and the sphere at this point are parallel. So if they do touch tangentially, the normals are going to be parallel. So we're just going to find the gradients and prove that they're parallel to solve this question. So let's see how it's done. So let the surface be phi1 and the sphere be phi2. If the surface and the sphere touch tangentially at a point, their tangent planes will be equivalent. However, it is much simpler and faster to prove that their normals are parallel, or their gradients at that point. So we've gone ahead and solved the gradients of the surface and the sphere, and then we've subbed in the point 1, 1, minus 2 to see what the gradient is equal to at that point. And here we can see that they are parallel, because if you times this one by 3, a scalar value, we get the gradient of phi1. So since the normals of the surface and the sphere are parallel at this point, the surface and the sphere do touch tangentially. Cool, so that's that question done. Okay, that's weird. Okay, so directional derivative. So I'll look at the theorem first. So this is just more the useful result we need to know. Like we get this result from this definition, because this kind of just represents the slope at a given the direction vector. So yeah, so the directional derivative of f in the direction u at a is given by the dot product of the gradient of f with the direction vector u. Okay, so the luminosity L at a point xyz in a galaxy is given by this equation. Find the rate of change of luminosity at this point in the direction of the vector v. So we're given a direction vector, and we have to find the rate of change with respect to a direction vector. So what should pop up in your minds is directional derivative, right? So the way we're going to calculate that is we're going to find the gradient of L, and we're going to do the dot product of the gradient with the direction vector. So part 2, in which direction does L change most rapidly at that point, and what is the maximum rate of change of L at this point? So from the theory, we know that if we look at the definition of the gradient, that the gradient is the direction of the steepest change. So the direction that L is going to change most rapidly at that point is going to be equal to the gradient, and you have to just sub in the point. And what is the maximum rate of change of L at that point? You just find the length of that direction vector. So yeah, so that's just how we're going to go ahead and solve this question. Recall that the directional derivative can be described geometrically as the rate of change of the function in the direction u. So we go ahead and calculate the gradient of L. So we've just factored out this part since each of the components will share this. And then now we're going to sub in the point, and we get this, the gradient. And when finding the directional derivative, we use the unit vector in the chosen direction. So we can't just straight away do the dot product of the gradient with the 1, 1, 1 vector. We need to normalize it. So you do 1 over the distance. So that's 1 squared plus 1 squared plus 1 squared. So that's the unit vector, unit direction vector we're going to do the dot product with. So hence the rate of change at this point is the dot product of the gradient with the normalized direction vector. And we get minus 1 and 4 over 3. So this means that at this point, the luminosity is decreasing at a rate of minus 1 and 4 over 3. In which direction does L change most rapidly at the point, and what is the maximum rate of change? So we already know that the maximum rate of change is going to happen at the gradient, which we already found, and the rate of change is just going to be the length of that vector, which comes out to be around 0.306. Okay, so Hessian matrix. So 2011 students are going to be kind of unfamiliar with this, but essentially we kind of apply the Hessian matrix in up to 2 variables only. So we only kind of look up to 2 by 2 right here. So this is kind of like fxx. This is fxx. This is fyx. This is fyy and fxy. So we do use like the Hessian matrix, but we just use a kind of simplified 2 by 2 version of it to find like critical points. And yeah, so I'll just, this is the 2111 content for Taylor polynomials and finding the first order Taylor polynomials. Okay, so maximum, minima, and saddle points. So if f is a function, then we know that a is a stationary point if the gradient is equal to 0. The global maximum, so the global maximum and minimum is obviously just when that function value is greater than all the other function values or less than all the other function values. And local minimum and maximum are more just a certain area. So it's just going to be like a disk where it's like a certain chosen area where it's the biggest or smallest function value. And a saddle point is a stationary point that's neither a maximum or a minimum. So these are the 2111 ways of finding critical points. But we're just going to look at the 2011 applications. So finding the Taylor expansion about a point x is this formula. So this formula is essentially just a result of the chain rule. So we know that for the Taylor series, we wanted to add the function value plus the first derivative over and the second derivative over the second factorial, and so on. So that's derived just from the chain rule. And if we expand this expansion formula for just up to the second order, so this is when n equals to 0. So when n equals to 0, this is going to be 0, so it's just going to be f. When n equals to 1, we get this, and this is when n equals to 2. Critical points. So for 2011, we say that a critical point is where the gradient is 0 or doesn't exist. And a stationary point is a bit more specific. It's where the gradient is equal to 0. So if you think about it intuitively, the reason why a gradient would be 0. So we said before that the gradient also represents the direction of steepest increase. So if you're at a maximum or a minimum, you're already at the top. So it's kind of the direction of steepest increase is just going to be a tangent plane, which is fully horizontal. And a function has a local maximum or minimum if it's the largest or smallest function value on some small disk. So yeah, a global maximum is for the whole space, but if we're looking at local maximum minimums, we just look at a certain disk. Okay, so to classify critical points as either local minimum maximums or saddle points, we use something called the second derivative test. So suppose the second order partial derivatives of f are continuous on a disk with center AB, and suppose that fx equals to fy equals to 0. So essentially, that sentence just means that we know that AB is a critical point. So we let the discriminant be equal to this. And essentially we just like pop in, we find what fxy, fxx, fyy are. We just pop in the values and then we just refer to this. So if this discriminant is less than 0, if fxx is larger than 0, then the point is a minimum. Otherwise, it's a maximum. And if the discriminant is larger than 0, then we know that the point is a saddle point. So looking at this question, let f be this function. Suppose that 1 minus 1 is a saddle point for f. So to prove this, we're going to use the second derivative test and prove that the discriminant is larger than 0. So we're going to have to find the second order partial derivatives and sub them in to find the discriminant. And if it's larger than 0, then we've proved that 1 minus 1 is a saddle point. So the second part is show that f has one other critical point and find out what type it is. So we know that critical points exist when the gradient of f is equal to 0. So we're just going to have to find the gradient of f, set it to 0, and see what other point we get. And to find out the type, we're just going to sub the point into the second derivative test to find the discriminant, and then we'll know what it is. And the third part, write down the Taylor series expansion of f about the critical point 1 minus 1. So we're going to calculate, the first, second, maybe third order partial derivatives of the function. And then we're just going to sub it into this formula to find the expansion. So cool. So show that 1 minus 1 is a saddle point. So we have the function. And then we go ahead and calculate the first order partial derivatives, the second order partial derivatives, and we see that fxx is equal to 6x plus 6. So you can actually, there's one third order partial derivative that exists. So we have these. So now, since we have these three second order partial derivatives, we can now find the discriminant at 1 minus 1. So here we have it. And then, yeah, so fxy at 1 minus 1 is going to be 24. fxx is going to be, 6 plus 6, so that's 12. And fyy is always 24. And we get that the discriminant is 288, which is larger than 0. So since the discriminant is larger than 0, we've proved that 1 minus 1 is a saddle point. Show that f has one other critical point and find out what type it is. So we find the gradient, as we discussed before, and then we're just going to solve it. So this part equals to 0, and 24x plus 24y is equal to 0. So we have like x equals to like minus y, something like that. We have something else, and then we sub it in to here. Yeah, and then if we solve it, we get the critical point 1 minus 1. We already knew that 1 minus 1 is a critical point from the question. And we get another critical point, 5 minus 5. So that's the other critical point that the question is asking about. And to find out the type, we're just going to do the second derivative test. So the discriminant of 5 minus 5, so it's just the same things. We just sub the values of the 0.5 minus 5 into the second derivatives, and we end up getting the discriminant is negative. So this means that it's either 5 minus 5 is either a local minimum or maximum. So now we have to look at fxx. So we know that fxx is 30 plus 6, which is 36. And since that's 0, by the second derivative test, 5 is a local minimum. Okay, so now write down the Taylor series expansion of f about the critical point 1 minus 1. So since we found all these first, second, and third order derivatives, we can essentially sub it into this formula. Yeah, so this is like fx, fy, fxx, fxy, fyy. And we know that we have just one third order derivative, so it's going to also be plus 1 on 3 factorial fx plus. So the rest is just going to be 0 because the coefficients, which are the third order partial derivatives, are all set to 0. So this is just going to be 0, 0, 0. Yeah, so we just sub in 1 minus 1 here. And here we have fx, fy, and the one single third order derivative. So we're just going to sub in the values of these derivatives at f1 minus 1. So for example, fx at 1 minus 1 is, I think it's going to be fx at 1 minus 1 is going to be equal to 3 plus 6 minus 24 plus 15. So that's what? 9 plus 15. That's actually equal to 0. So fx 1 minus 1 is equal to 0. Yeah, and here we can see that there's no value that has like a number in front of x minus 1. So we can see, yeah. So we're just going to do the same thing. We're going to find fy at 1 minus 1 and all these derivatives at 1 minus 1 and just like sub them in. And then this is what it simplifies out to. Okay, so Lagrange multipliers. So suppose we have a function and a constraint. So this is going to be the function. It's going to be the constraint. If f attains a local maximum or minimum at a point, a part of the surface or the constraint, then the gradient of the function and the gradient of the constraint are parallel. If the gradient of the constraint is not equal to 0, then there exists a Lagrange multiplier such that the gradients of the function and the constraint are going to be parallel. So if we think about how this function looks intuitively, so if we have like say like contour lines of a like level lines of a hill, so this is right at the top and this is a bit lower down, so on, and we have a constraint which is might look like this. So we know from earlier that say at this point the gradient is going to point to the direction of steepest increase, so it's going to look like this. But because we have to find a point f which satisfies the constraint, so that the constraint and the function have to meet. So maybe somewhere down the line they touch right here. and we're going to have the gradient of f is going to point perpendicular to the tangent line. So it's going to point to the direction of the steepest increase. And the gradient of the constraint is going to do the same thing. So yeah, so that's kind of intuitively why this formula exists. So these two vectors are going to be parallel with some kind of multiply, because we don't know if they're equal or not. Okay, so exam question. A rectangular box has 3 of its faces on the coordinate planes and 1 vertex in the first octant on the paraboloid. So this is the constraint, and determine the maximum volume of the box. So it has 1 vertex in the first octant. So in the first octant, I'll take it to be where x, y, and z are larger than 0. So if we kind of draw it up, so this is x, y, z. So yeah, and we have the paraboloid, z equals 4 minus x squared minus y squared. So what does that look like? So when x and y is equal to 0, z equals to 4. And when z is equal to 0, x squared yeah, so this is when x and y is equal to 0, and when z is equal to 0, we have a circle with radius 2. So this paraboloid is going to kind of look like this. And if we take this region to be the first octant, so if this is where x is larger than 0, y is larger than 0, and z is larger than 0, so one of the vertices are going to be on here. So it could be this point, and the rest of the faces are along the coordinate plane. So it just goes across like this. Actually, that's kind of a bad point. Maybe if the point is here, then yeah, we have a face on the YZ plane, the XZ plane, and the XY plane here. So the point here is going to be equal to XYZ. So the volume of the box is going to be X times Y times Z. So that's where we get this function. And the constraint, that's what we're given. Okay, so now we know we have to find the gradients of f and g, or the constraint. So here we've calculated this. So just for the first one, since f is equal to x, y, z, yz is essentially fx, and this is fy and fz. Here's gx, gy, and gz. And now check that the gradient of the constraint is not equal to 0. And since we have a -1 here, this is never going to be true. So why is the fact that the gradient of the constraint having to be non-zero important? Because if we go back to the fact that we need the gradients to be parallel, it's going to be a little tough if the gradient vector is just 0. And we know this, and we found the gradient of f and gradient of g, and we know this is just a constraint. So it gives us these equations. So if we just go back real quick, yz is going to be equal to lambda times minus 2x. Xz is going to be equal to lambda times minus 2y, so on. So that's how we get these equations, and this is just what the question gave us. So at this point, we want to solve the values of x, y, and z. So you just have to be creative with your algebra and just try to cancel out and try to get this equation or whatever in terms of just one variable. So you can find what, say, z is equal to first, and then sub value of z into x and y to find x and y. So what I did first was just to divide the first equations by the third. So just doing this one, we have yz equals to minus 2 lambda x, and if we divide it by this one, the third equation, this cancels out to get z on x is equal to x, and there we get x squared equals z on 2. And similarly, we get y squared is equal to z on 2. So now we go ahead and look at this equation, and then we can see that we can sub x squared and y squared into this equation to get an equation just in terms of z. So now we know what the value of z is. So substituting into the constraint, we get that 2z is equal to 4. So z is equal to 2. So yeah, and then given z equals 2, we just sub it in here. So x squared equals to 2 on 2 is equal to 1. Y squared equals to 1. And since the point is on the first octant, x and y are larger than 0. So x equals to 1, y equals to 1. So the point is 1, 1, 2, and thus the volume is, the maximum volume is going to be 2, because that's just 1 times 1 times 2. Okay, so it's just one more question. So the inverse function theorem. So I'll look at the 2011 version. So if f is differentiable at A, then if the Jacobian matrix at A is invertible, so if we remember how to invert a matrix, we know that it's going to be 1 over the determinant, and then we're going to switch around these elements. But for an invertible matrix to exist, the most important part is just to ensure that the determinant is non-zero. There is an inverse function to find in some neighborhood of b equals fa. Okay, so let f be given by this. So find the Jacobian matrix. So I think J went over a similar question of just solving the matrix before. So we're just going to do solve f1, which is, this is f1, this f2. So we're going to solve f1 with respect to, differentiate it with respect to the first component, which is f. So df1 dx, df1 dy, yeah, so this is just going to be equal to 2x plus 1. So we're just going to do that for all the elements of this matrix. So yeah, we get this. So the second part is, what does the Jacobian at point 00 and the inverse function theorem tell you about f around 00? So we're just going to first find that matrix to see what it is first. And if we just sub in 0, 0, we get this matrix. And the determinant is 1 times 3 minus 2 times 0. So that's 3. And since that's non-zero, we can invert this matrix. And thus, by the inverse function theorem, f will have a inverse around f. That brings me to the end of differentiable functions. I don't know if we'll have that much time to do this part. But yeah, I'll end it here for now.
Hello? Can you all hear me? Alright, I think I can see myself on the stream, that's good. Alright, yeah, so we might go a little over time. We still have a section left on integration. We might go up until maybe around 4:15, 4:20ish. Hopefully that won't be too bad for all of you. If you guys do need to leave, you guys can watch the recording after. Okay, so let's get started then. So for integration, we're going to start off with upper and lower sums. This sort of concept doesn't really come up in exams at all, but I'll just do a quick illustration of what upper and lower sums mean. For example, S with a bar on the bottom means the lower sum. S with an upper bar on the top means the upper sum. And visually, it just means that if you have some sort of function, let's say like this, if you draw rectangles, I'll use different colors. I'll use red for lower sum and green for upper sum. For example, rectangles like this, as compared to rectangles, okay, it's orange, like this. And so on. These orange rectangles will constitute the upper sum, and the red rectangles will constitute the lower sum. And so basically, the actual integral is so the actual area on the curve sits between the sum of areas of the upper rectangles and the lower rectangles. Okay. So a Riemann integral is basically, like I said before, the value of the integral that lies between the lower sum and the upper sum. Okay. Okay, a region D is y simple if there exists a continuous function phi1 and phi2 such that phi1 is less than phi2 for all x between a and b. And that's denoted in the notation here. And x simple is similarly defined. What does it look like? For example, a y simple function would look like something like this. This would be a y simple region. Why is it y simple? Because it's exactly vertical in the y components. Okay, and furthermore, this function on top would be called phi2. The function on the bottom here would be called phi1. Okay, so phi2 is greater than phi1. X simple would just be the same thing, but other way around. So the EX components are straight lines. Okay. Okay. Some properties of integrals. We'll just briefly mention them. If f and g are integrable on the region D, then I guess the linear combination of f and g will just split off to be a integral of f plus b integral of g. The absolute value of the integral of f is less than or equal to the integral of the absolute value of f. Okay. Again, this should kind of make sense because, I guess for example, if you have a function like a cube like this or something, this would be the absolute value of the sum of these areas, whereas the integral of absolute value of f would be after you have reflected this onto the top, and after you have reflected this onto the top, then it's going to be this area here. Right. So obviously the orange area is going to be greater than the red area because the red area has negative areas before you take the absolute value. Okay. Okay. And finally, if we can split the region into a union of two other regions, then the integral of f. Oops. Why did I draw that? The integral of f would just be the integral of f over each region individually, add up together. Okay. Fubini's theorem says that if f is continuous on a rectangular domain, then we can rearrange the integral, right? So loosely speaking, it's just saying as long as this above condition, so this condition here, is satisfied, then we can just manipulate and rearrange the integral however we want. Okay. So first example here, consider the Euler-Poisson integral. So I equals the integral from 0 to infinity of e to the power of negative x squared dx. Using Fubini's theorem, prove this. Okay. So we're looking at I squared here, and usually for a proof question, you kind of want to start from one side and get to the other side. In this case, let's start with our right-hand side because it looks more complicated, and we'll try work backwards to try get to I squared, or in other words, we're going to try get this here. Okay. All right. So how can we approach this? Firstly, note that the integrand, so the integrand here, is a continuous function for all of R2, right? At no point will there be any breaks or asymptote. It's e to the power of negative x squared, negative y squared. So it will be continuous across the entirety of R squared. Okay? And so we can apply Fubini's theorem, right? So we can apply Fubini's theorem here. Okay? So firstly, we have that our right-hand side, this is our right-hand side, equals to, I'll just copy that down from before, a quarter integral blah blah blah. And this equals to a quarter of integral negative infinity to infinity integral negative infinity to infinity of e negative x squared minus y squared dx dy. I basically just broke up r squared into two integrals from negative infinity to infinity on the y-axis and negative infinity to infinity on the x-axis. Okay. Now note that this is an even function, right? So if I plugged in f of negative x, it would still just be this, which is still fx. Right? So it's an even function, and so we can bring in our quarters to I guess I'll do it up here. It's as if I got rid of this a quarter and I chucked a half here, and I chucked a half here. Then because the function's even, this half allows me to turn negative infinity to just the 0 to infinity and 0 to infinity. Okay. This stuff on the inside is still unchanged. Then by Fubini's theorem, we can again rearrange and manipulate our integral however we want. So we're gonna bring this e to the negative x squared bit outside and leave e to the power negative y squared on the inside for the integral with respect to dy. Okay? And we're gonna have this integral 0 to infinity e to the power negative x squared in terms of dx. Okay? Okay. And notice that, hopefully you guys have already noticed, but this thing here is really just I. Right? If we go back, I was this. So it's kind of like we just have a dummy variable instead of x we have y, but it's actually really just the same thing. It's really just the same as this, right? So this part here we have already deduced is actually I. Okay, so we chuck I outside, so we brought it outside, and now we just have the integral from 0 to infinity of e to the power negative x squared dx. But again, notice that this is again just I. So eventually we have equals to I squared. Okay, and that's it. So we went from right hand side to left hand side. Okay. Next, iterated integrals for elementary regions. Suppose D is a y-simple region bounded by x equals a, x equals b, y equals phi 1x, and y equals phi 2x, and f goes from D to the reals and is continuous. Then we have that the integral of f over the region D is equal to this. Right? It's really just the same concept as how I turned integral over r squared into two different integrals over two different boundaries. Yeah. So if I illustrate this, it's saying if I have a y-simple region, so this is phi 2, this is phi 1, and this is x equals a and x equals b. I'm just integrating my my x values. I think this actually might be the wrong way around. I think it's Yeah, I think it might be dy dA dx. Right? Let me write this properly. dy dx. Okay, so we're integrating over y the phi2 function minus the phi1 function. So from phi1 to phi2, that would be, for example, one interval here, phi2 minus phi1. And then once we take that, then we integrate across all possible values of x, so from a to b. Okay. Okay, next we have Leibniz's rule, which is also called differentiation under the integral sign. Let a and b be reals and be constants, and say that a is less than or equal to b, and phi1 and phi2 is essentially from an interval to a real number, be a continuous function, such that phi2 is greater than phi1 for all values of x. If f and the partial derivative of f are continuous on the region D, then the function gx has this derivative. You're not really required to prove this, just need to know it, right? Differentiation under an integral sign is a special case of this when phi1 and phi2 are just constants. So let's say if it was just b and a, then this would be differentiation under the integral sign instead of Leibniz's rule. They're really just the same thing, right? But if you do have boundaries that are also with respect to x itself, then you have to have these extra terms here. So I'll highlight it with red, this one here, and this term here. Okay, there's just extra terms you have to tag onto your differentiation on an integral sign if you have boundaries that depend on x as well, or depend on the variable you're differentiating with. Okay. So yeah, notice in differentiation under the integral sign, these terms here do not exist because phi2 and phi1 are simply constants. So the differentiation of a constant is just 0. That's why that term is gone, causing this term to be gone, and this term is gone, causing this term to be gone. Okay, but the full Leibniz's rule is as stated here. Okay, let's move on to some applications. So I guess some questions related to Leibniz's rule. Move on to the next page. Okay, so calculate d on dx of this integral here from x to x squared of the function cos xy over y dy for all x greater than 1. This question is essentially a direct application of Leibniz's rule. Yeah. So whenever you see something like this where you have a derivative of an integral, you pretty much just instantly resort to thinking, okay, it has to be either Leibniz's rule or differentiation on an integral sign. Okay? So let's firstly check the conditions to make sure that we can apply Leibniz's rule. Firstly, we have that the integrand, so your cos xy over y. So I guess I'll write it here again. Cos xy over y is continuous across the entire boundary for x greater than 1. And furthermore, that furthermore that y lies between x and x squared for x greater than 1. Right? So remember our boundaries are x and x squared. This is like our phi 2, and this is like our phi 1. Okay? So it satisfies all the conditions, it's continuous, and furthermore, the thing we're differentiating with respect to lies between phi 1 and phi 2. Okay? And so we can apply Leibniz's rule. Right? And alright, no, my bad. Furthermore, we have to check one more thing. We have to check that the partial derivative is also continuous. df on dx is also continuous. So let's take the partial derivative of cos xy on y, okay, in terms of x. So we're taking the partial derivative, so only this x here is affected. So we bring the y out due to chain rule, and then negative sine xy, and the denominator of y stays the same. That cancels, so we just get negative sine xy. And obviously negative sine xy is still continuous everywhere. And therefore we have all the conditions satisfied. The integrand is continuous, the partial derivative of the integrand is continuous, and our y lies between our two phi's, phi 2 and phi 1. Okay? So, a direct application of Leibniz's rule, we have this component being the differentiation under the integral sign component. Then we have this component being our function evaluated at phi 2 of x times by the derivative of phi 2. And we just have this term here, which is our function evaluated at phi 1 of x times by the derivative of phi 1 of x. Right? So in this case, we have g evaluated at x squared. So cos x, x squared over x squared, we replace all y's of x squared, times by the derivative of x squared, which is 2x, minus cos x of x over x, because this time we replace all y's of x's, times by the derivative of x, which is 1. Then we just simplify this stuff. So we get 2 cos x cubed on x, because this x and this x cancels. And we get cos x squared on x, because this one disappears. And here we have the partial derivative in terms of x. So cos xy over y partial derivative in terms of x, we calculated before, equals negative sine xy. So we chuck that in. Then we just evaluate integral. Right? We're integrating in terms of y. So due to the chain rule residue, we get 1 on x on the outside. And our sign turns into cos xy. Notice that the negatives from here and from the integral of sine cancels. And then we're evaluating it for y between x and x squared. We chuck that in, we simplify further, and we end up with this answer. Okay? Alright, let's move on. Another example of Leibniz's rule, or in this case differentiation under the integral sign, because our boundaries are no longer dependent on x. This is another very common example in exams. It's kind of a bit more difficult than this because you have to think about what you're trying to do, right? So this is just a direct application of the rule. In this case, you have to kind of invoke the rule yourself. You have to force it to become possible to use Leibniz's rule, right? So we're using differentiation under the integral sign to find this value when we're given this. Okay. Notice there's quite a lot of similarities between the two. If a was 2, we would pretty much have the same integral. So if a was 2, we would pretty much have the same integral, except we're missing a squared here, right? We don't have the squared here. Yeah? So how do we deal with that? Well, when we apply Leibniz's rule, or when we try to apply Leibniz's rule, at the moment, it would be very annoying to apply Leibniz's rule on x, right? Imagine trying to do this. Let's write it out. Right? Imagine trying to do this. Firstly, this wouldn't really work because we have d on dx of dx, or of the integral of in terms of dx. And furthermore, if you did bring it in with differentiation under the integral sign and perform the partial derivative, you would get an expression even more complicated than what we started with by a long mile, right? You would have to apply quotient rule, and you would get something that's very long, right? And so instead, our idea is that we want to invent a new parameter to perform differentiation under the integral sign for. And in this case, why not choose a? Right? A is another parameter in our integrand that we can choose to differentiate over. Right? So instead, we're going to differentiate over dA. Okay? Let's see what this results in. All right? So if we take the derivative of this integral in terms of a, we have to take it on both sides, obviously, because it's an equation. So we take it on our right-hand side as well, which was pi on 8 e to the power of negative 3a. Then we end up with, on the right-hand side, we have to apply, what is this? I think I apply a product rule here. I just turned this to pi a to the power of negative 1 e to the power of negative 3a. Okay. Then I apply product rule and end up with this. And then on my left-hand side, I can bring my integral in via Leibniz's rule, or due to differentiation under the integral sign. And now I'm just taking the partial derivative of this in terms of a, which is much simpler than doing it in terms of x. Right? And furthermore, notice when I do it in terms of a, I perfectly get this x squared plus a squared to the power of 2 on my denominator, right? Reason being, I have something of this form. So when I take the derivative, it should become this, right? So I get this denominator to the power of 2 now, which is what I want, right? I eventually want this, okay? Okay, so we take derivative on both sides. That's what we get. This negative 2a has nothing to do with dx, so we can just bring it out and divide it over, and that ends up giving us this result, right? We divide the negative 2a over, so it comes onto the denominator, and furthermore, the negative from here cancels out with the negative from here. Okay, so we end up with this expression. And finally, notice, like we said before, now this integral is really just like the integral that we want, except we should replace a with 2. Once we replace a with 2, this will exactly become this. Which is the integral that we want to compute. Okay? And so we chuck a equals 2 in, and we evaluate it, and we end up getting 716 pi e to the power of negative 6. Okay? Alright? That's pretty much like the most common type of questions for Leibniz's rule and differentiation under the integral sign. There will be these direct application questions, and there will also be these questions where you have to kind of invent your own variable. Okay, let's move on. Another technique of integration is called the change of variable. Let omega be an Rn and f be a function that's injective and continuously differentiable such that the determinant of the Jacobian of f is not 0 for all x's. If f is any function that is integrable on omega dash, which is f of omega, then the integral over this region f composed of like lowercase f composed of uppercase f times by the determinant, the absolute value of the determinant of the Jacobian of f is how you would evaluate the integral. Okay. So it's kind of a way for you to change the variable of integrals. So whether it was dx dy, for example, if this was dx dy, sorry, maybe not here. Let me write this a bit more properly. For example, if you were being asked to evaluate, just, I guess, oops, not dash, being asked to evaluate this integral here, and let's say it was initially in terms of x and y, we can now use this transform, I guess we could call it the Jacobian transform, and turn it into whatever we change our variables to, let's say du dv. Okay, so then we have a way to change our variable that could perhaps make the calculation easier if we change the variables to du dv, or whatever we want to change it to. Right? In this case, a very common substitution is like, for example, polar substitution. Right? We can change our x to r cos theta and y equals r sin theta. Then after our Jacobian transform, it will turn into dr d theta, or d theta dr, either one. Yeah. There will be more examples of polar substitution on Wednesday when we go through line integrals and path integrals. As for today, we'll go through an example that isn't polar, it's just a more generic example. Okay. So we want to evaluate the integral over the region omega dash of x squared dx dy. Okay, where this region omega dash is the first quadrant lying between the hyperbolas xy equals half and xy equals 2, and the two straight lines y equals x and 2, y equals 2x. Okay, so how does this region look like? It looks like this. All right, so it's graphed on Desmos. You can notice that these two are your hyperbolas, and these two are your straight lines. Okay, so the region bounded in between. Okay, so how can we make some substitutions and change of variables? Then how do we then apply a Jacobian transform to get this form here. Okay, let's have a look. So, since our regions are bounded by functions in terms of xy and y, right? Remember we have xy bounded by half and 2, y bounded by x on 2 and 2x. Intuitively, we want to replace the xy's and y's. Or like more importantly, we want to replace xy, because that's annoying to deal with. So we'll make the sub u equals xy and just v equals y. Okay? We can re-express x in terms of u and y in terms of v, well y is simply just v. And furthermore, x is equals to u, oops, what happened here? X is equals to u on y, but y equals v, so it's equal to u on v. So we get this result as well. Okay? And now we have to apply our Jacobian transform, or like our Jacobian matrix. So we're going to take the partial derivatives of our x in terms of u and v, and our y in terms of u and v. So the derivative of our x in terms of u, maybe I'll just write it down here again, x equals uv, y equals to v. The derivative of u in terms of, the derivative of x in terms of u becomes 1 on v. Derivative of x in terms of v equals to, this is a bit of a typo, I think it's meant to be negative u on v squared. Okay, I'm not sure why it's missing a u here. Okay, it should be negative u on v squared. Then we differentiate y in terms of u, that's just 0, and we differentiate y in terms of v, that's just 1. And so the determinant of this matrix would just be 1 on v times 1 minus, or in this case plus, u on v squared times 0, which is just 1 on v. Okay? So we now have nearly all the components to our Jacobian transformed integral. We have our determinant, and now we just have to do f composed of capital F. Right? So let's keep going. Firstly, note our changes in our boundaries. U lies between half and 2. Why is that? That's because we had our hyperbolas lying between half and 2. And we also have v lying between u on 2v and 2u on v. Why is that? Well, that is because our y lied between, I believe, x on 2 and 2x. Let me double check that. Okay, y lies between x on 2 and 2x. And so we have y, lying between these two functions. But since our x equals to u on v, this just becomes u on 2v, and this just becomes 2uv. Okay? And furthermore, we can simplify this a little bit more. Cross times the v's over, and then take square roots, and you end up with v lying between root u on 2 and root 2u. Okay? So now we have all the boundaries set up as well. We have our Jacobian. Let's just plug it all in. Right? So these are our boundaries, our new boundaries, half to 2, and root u on 2 to root 2u. This is our determinant of the Jacobian. And this here is f composed of capital F. Why is that? Okay, so why is that? Remember our lowercase f, which is x squared. Remember our capital F. What did our capital F become again? Alright, I don't know. Our capital F was basically just transforming our x's into u's, right? And we had managed to transform our x into u and v, and our y into just v. So therefore, now it becomes x squared, which is u on v bracket, u and v bracket squared. Okay, so this is our f composed of capital F. Okay. We evaluate the integral on the inside first in terms of v, right? So this would become the integral on the inside. This would become root u on 2, root 2u, and this would be u squared on v cubed dv. Okay? And we would evaluate that, and we end up getting this. Then we plug in our root 2u and root u on 2. Okay, we simplify this, and we end up getting 3 on 4u. Then we finally evaluate the integral one more time, the outer integral this time, from half to 2, and we end up getting 45 on 32. Alright? And yeah, that pretty much concludes it. Right, that concludes it for integration as well. So again, I guess a brief overview of what we did today. If I can use my cursor. We went through curves and surfaces, points at topology, differentiable functions, and integration. On Wednesday, we'll be going through the remaining 4 topics. I'll be covering Fourier series, and Steve will be covering chapter 6 through to 8. Okay. If any of you guys have any further questions on any of the topics covered today, then you can feel free to stay behind. I'll stay for another about 5 minutes. But besides that, you're all free to go. Thank you for coming today, and hope to see you guys on Wednesday as well. Yep, no worries. Thank you for coming. Yep, thanks Sarah for coming. Alright, I think if no one else has any questions, I'll probably end the stream now. Alright, bye bye.